We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard.
Godspeed, John Glenn.
Roger, 0G, and I feel fine.
Get my feet out. Okay, I'm out.
How does it feel for the United States to be the new record holder?
At last, huh? When that baby lights, there's no doubt about it.
Liftoff. We have a liftoff. 32 minutes past the hour. Liftoff on Apollo 11.
Houston, Tranquility Base here. The Eagle has landed.
That's one small step for man, one giant leap for mankind.
Hello and welcome. This is Michael Annis, and you are listening to episode 121 of the Space Rocket History Podcast. And now, Pegasus wings inside SA-8, 9, and 10, and a command module update for 1965. The first part of this episode is a continuation of the Saturn I test flights that have been covered in episodes 104, 105, 109, 111, and 115. I'm going to begin with the cargo for SA-8 through 10. That was the Pegasus satellite. You may recall from earlier episodes that there was a great concern about meteoroid impacts to the Apollo spacecraft while traveling around the Earth and to the Moon. NASA needed to know how much shielding would be required to prevent damage to the spacecraft, which brings us to Pegasus. The Pegasus satellite program was a series of 3 satellites launched in 1965 to study the frequency of micrometeorite impacts on spacecraft. All 3 Pegasus satellites were launched by Saturn I rockets and remained connected with their upper stage, which was the S-4 stage that I covered last week. The Pegasus satellite was named for the winged horse of Greek mythology. Like its namesake, the Pegasus satellite was notable for its wings, a pair of 29-meter-long, 4.3-meter-wide arrays of 104 panels fitted with sensors to detect punctures by micrometeoroids at high altitudes. In its stored position, with panels folded inside the Apollo service module, the Pegasus was 5.3 meters high, 2.1 meters wide, and 28 centimeters deep. It was the largest satellite launched up to that time, and the first active payload launched by a Saturn vehicle. Pegasus was divided into 2 major parts: the central section and the wing assemblies. The central section was attached to the launch vehicle's second stage. It provided a mounting place for the deployment mechanism, electronics canister, solar power panels, and sensors. Total weight in orbit was 10,500 kilograms. The Goddard Space Flight Center's Space Tracking and Data Acquisition Network tracked the satellite using the signal of the telemetry transmitter that transmitted continuously on 136.89 megahertz. Optical tracking coverage was provided by the Smithsonian Astrophysical Observatory's Optical Tracking Network and the Minitrack Optical Tracking System. Of course, the main reason for Pegasus was micrometeoroids were believed to be potentially hazardous to the Apollo crew if they could puncture the spacecraft's skin. These sensors were used to measure the frequency, size, direction, and penetration of micrometeoroid impacts. The impact sensors were based on a charged capacitor with a thin dielectric, featuring metal foil on one side and a sheet of aluminum on the other. When struck by a meteorite, a brief short between the metal plates was created, with the discharge burning off the resulting conducting bridges between the metal layers and effectively repairing itself in the process. It was this discharge that was recorded as a hit, with onboard sensors relaying information on the frequency and size of the meteoroid and its trajectory. That provided an indication of the power of each recorded hit. The satellite also carried sample protective shields mounted on the arrays. Engineers could compare the performance of protected and unprotected solar cells. This data was important because scientists needed to characterize the environment, including micrometeoroid hazards that might damage the Apollo capsule. Marshall Space Flight Center was responsible for the design, production, and operation of the 3 Pegasus satellites. Fairchild Stratus Corporation in Hagerstown, Maryland, made the panels. Now I have an audio clip on the Pegasus.
The 18-story Saturn I stands on its pad at Cape Kennedy, poised to send Pegasus 2 into orbit. The world's most powerful rocket lights up the landscape as it generates its 1.5 million pounds of thrust. The Pegasus 2 follows a twin into orbit. Pegasus 1 and 2 are measuring the density of meteoroids. This is important data to have collated before we send our astronauts far out into space, much further than the current project, Gemini 1. Animation shows how the Pegasus goes through its paces once the hydrogen-powered second stage puts it into orbit, an orbit ranging from 316 to 460 miles high. When the satellite is comfortably in place, it goes into action on its own to thrust out wing-like panels to a span of 96 feet. These will measure the damage tiny meteoroids might cause as they hit a spacecraft with sandblast effect while they speed through the reaches of outer space.
Now it's time to move on to SA-9. SA-9, also known as AS-103, was the 3rd orbital test flight of a boilerplate Apollo spacecraft. The first flight of a Pegasus micrometeoroid detection satellite, and it was the 3rd operational launch of a 2-stage Saturn I launch vehicle. You may recall from the first 7 SA flights that this vehicle used the S1 first stage with the 8 H1 engines powered by RP1 kerosene and liquid oxygen. The second stage was the S4, which had 6 more sophisticated RL-10 liquid hydrogen, liquid oxygen engines that I covered in episode 120. Now you may be asking, why am I covering SA-9 before SA-8? Well, SA-9 was launched before SA-8. This was because of delays in the industrial contract manufacturing process in which the booster designated for SA-8, supplied from contractor Chrysler, was delayed, being the final stage developed and built at Marshall. SA-9 was therefore ready before SA-8, and as a result, flew first. SA-9 was also a departure from the previous Block 2 Saturn I missions with the inclusion of the Pegasus satellite. This flight also included a command module boilerplate, BP-16, and a launch escape system. There were 12 flight objectives assigned for SA-9. 2 were concerned with the operation of the Pegasus satellite, 8 with launch vehicle systems performance, 1 with jettisoning the launch escape system, and 1 with separation of the boilerplate spacecraft. The satellite objectives were 1. Demonstration of the functional operation of the mechanical, structural, and electronic systems, and 2. Evaluation of meteoroid data sampling in near-Earth orbit. Since the launch trajectory was designed to insert the Pegasus satellite into the proper orbit, it differed substantially from the trajectory used in missions SA-6 and SA-7. Before launch, there was a hold of 1 hour and 7 minutes caused by a power failure in the Eastern Test Range flight safety computer. A built-in hold of 30 minutes was also used to discharge and recharge a battery in the Pegasus satellite as a check that it was functioning properly. After the delays, SA-9 lifted off from Launch Complex 37B at 9:37 a.m. Eastern Time on February 16, 1965. The launch vehicle consisted of the S-1 first stage, an S-4 second stage, and an instrument unit. The spacecraft consisted of the boilerplate command and service module, a launch escape system, and a service module launch vehicle adapter. The Pegasus satellite was enclosed within the service module attached to the S-4 stage. The boilerplate command module and service module acted as a shroud to hold the Pegasus satellite. The orbital configuration consisted of the satellite mounted on the adapter, which remained attached to the instrument unit, and the expended S-4 stage. After first stage separation and second stage ignition, the launch escape system was jettisoned. When the second stage attained orbit, the 4,500 kilogram Apollo boilerplate command and service modules were jettisoned into a separate orbit. Then a motor-driven device extended the wing-like panels of the Pegasus to a span of 29 meters. The Pegasus wings remained attached to the Saturn I's second stage as planned. The launch was normal and the spacecraft was inserted into orbit approximately 10.5 minutes after launch. A television camera mounted on the interior of the service module adapter provided pictures of the satellite deploying in space and the wings extending. The satellite exposed more than 210 square meters of instrumented surface. The total mass placed in orbit was 15,375 kilograms. The orbital perigee was 495 kilometers, and the apogee was 743 kilometers, and the orbital inclination was 31.76 degrees. The results of the flight were good. The trajectory and space-fixed velocity were very nearly perfect. The Apollo shroud separated from the Pegasus satellite at about T plus 804 seconds after liftoff, and deployment of the two meteoroid detection panel wings of the Pegasus satellite commenced about a minute later. In the first 3 months in orbit, Pegasus 1 recorded 70 meteoroid penetrations of the panels, and it was planned for each satellite to remain in orbit for at least a year. Although Pegasus 1 exceeded this by remaining in space until September 17, 1978, several years after its mission had ended. Although minor malfunctions occurred in both the launch vehicle and the Pegasus satellite, mission AS-103 was a success in that all objectives were met. Moving on to SA-8. SA-8, also known as AS-104, was the fourth orbital test of a boilerplate Apollo spacecraft, the second flight of the Pegasus micrometeoroid detection satellite, and the ninth Saturn I flight. The primary mission objective was to demonstrate the launch vehicle iterative guidance mode and evaluation of system accuracy. The launch trajectory was similar to that of mission SA-9. The Saturn launch vehicle, SA-8, and payload were similar to those of mission SA-9 as well, except that a single reaction control engine assembly was mounted on the boilerplate service module, and the assembly was instrumented to acquire additional data on launch environment temperatures. SA-8 was the first nighttime launch in the Saturn I series. A built-in 35-minute hold was used to ensure that launch time coincided with the opening of the launch window. SA-8 was launched from Cape Kennedy Launch Complex 37B at 2:35 a.m. Eastern Time on May 25, 1965. The launch was normal. After first stage separation and second stage ignition, the launch escape system was jettisoned. After the second stage attained orbit, the 4,400 kilogram boilerplate 26 was jettisoned in a separate orbit, which was about 10.6 minutes after liftoff. The total mass placed in orbit, including the spacecraft, Pegasus 2, adapter, instrument unit, and S-4 stage, was 15,473 kilograms. The orbital perigee was 505 kilometers, and the apogee was 747 kilometers. The orbital inclination was 31.78 degrees. The actual trajectory was close to the one predicted, and the spacecraft was separated at T plus 806 seconds after liftoff. Several minor malfunctions occurred in the S1 stage propulsion system, and intermittent failures occurred in the telemetry channels, but stable communications were reestablished. All mission objectives were achieved. The second Pegasus satellite also remained in orbit far longer than planned and eventually re-entered on November 3, 1979. With the flight of SA-8 complete, we will now move on to SA-10. SA-10, also known as AS-105, was the fifth and final orbital flight of a boilerplate Apollo spacecraft, the third and final launch of a Pegasus micrometeoroid detection satellite, and the 10th and final Saturn I rocket test flight. Similarly to previous flights, the primary flight objective was to continue demonstration of the launch vehicle's iterative guidance mode and evaluation of system accuracy. The Saturn launch vehicle SA-10 and payload were similar to those of the SA-8 and 9 missions, with a notable exception. The Pegasus satellite on this flight had the added feature of 8 large removable detector segments that could theoretically have been visited by later Gemini crews, but of course that never materialized. SA-10, also known as AS-105, used boilerplate BP-9A, and like the previous two flights, the S-1 first stage and the S-4 second stage. As on the previous mission, the boilerplate service module was equipped with a test installation of a reaction control engine package. The launch was moved forward from its original date in order to clear the Launch Complex 37B area for modifications and preparations to support its use for the first Saturn IB unmanned missions. A planned 30-minute hold ensured that launch time coincided with the opening of the Pegasus launch window. SA-10 was launched from Cape Kennedy Launch Complex 37B at 8 a.m. Eastern Time on July 30, 1965. The launch was normal, and the payload was inserted into orbit approximately 10.7 minutes after liftoff. The total mass placed in orbit, including the boilerplate, Pegasus satellite, the adapter, the instrument unit, and the S-4 stage, was 15,621 kilograms. The orbital perigee was 521 kilometers, and the apogee was 536 kilometers. The degrees of inclination was 28.28 degrees. The spacecraft was separated at T plus 812 seconds after liftoff. The separation and ejection system operated as planned. The Pegasus 3 spacecraft, which was attached to the S-4 stage and stowed inside the boilerplate service module, was deployed 40 seconds after command initiation at T plus 872 seconds. In comparison with prior missions, the spacecraft remained in orbit only a short 4 years and re-entered the atmosphere on August 4, 1969. In summary, as far as Pegasus was concerned, NASA received much more information than they thought they would. Of course, all 3 Pegasus missions provided the expected data on micrometeoroid penetration, but scientists were also able to gather data regarding gyroscopic motion and orbital characteristics of rigid bodies in space, lifetimes of electronic components in the space environment, and thermal control systems and the degrading effects of space on thermal control coatings. For physicists, the Pegasus missions provided additional knowledge about the radiation environments of space, the Van Allen radiation belts, and other phenomena. As for the SA test flights, all the Saturn I launches were completed successfully and set the precedent for the whole Saturn family of launches through 1975. By the time of the second Saturn I launch, the Saturn V was under development and the Saturn 1B was being prepared to launch a series of Earth orbital developmental flights that would test the manned Apollo and the S-4B stage, which would be used in the Saturn V to take the lunar missions out of Earth orbit towards the Moon. At the time, there was criticism about NASA that the Saturn I series was a program with no real objective, and that Project Highwater and the Pegasus satellites were included merely to demonstrate limited scientific return from the developmental program. But, looking back at the program, it can be argued that the work of the Marshall engineers early in the program helped in the success of the Saturn series throughout pre-launch testing and checkout prior to the final launch preparations. It also saved time and money and directly provided experience in several areas relating to later Saturn 1B and Saturn V missions, and in manned spaceflight development in general. Experience was also gained in preparing the Saturn liquid hydrogen stages, the demonstration of ground processing of cluster rocket engine configurations, early versions of the guidance and control systems, boilerplate Apollo spacecraft and test of the launch escape systems, and processing cycles at the Cape and the launch tracking network, and additionally the bonus experiments of Project Highwater and the Pegasus satellites. Changing the subject, it has been a while since I spoke of the command module, so the following is an update of the command module for 1965. In 1965, command module weight was continually getting out of hand. Caldwell Johnson reminded Max Faget in August that more than a year and a half earlier, he had pointed to weight control as the single most difficult technical problem. To keep the spacecraft on its diet, Johnson proposed putting pressure on the subsystem managers to begin a rigorous system of checks and cross-checks down through the subsystem level. Faget passed Johnson's suggestions along to NASA manager Joseph Shea, who already was aware that he had a fat spacecraft. Shea was also being bombarded with warnings about the lack of reliability in the Block 1 command module. Owen G. Morris, Shea's chief of reliability and quality assurance, listed 71 possible failure points that North American had evidently done nothing to eliminate. Morris was not the only person to raise the reliability issue. Shay's old adversary in the mode selection debate, Nicholas Golovin of the President's Science Advisory Committee, wrote that he had heard of 50 items that accounted for 95% of the unreliability of the Apollo system. Not all the stories were bleak, however. In November, attention centered on a 3-week critical design review for the Block 2 command module. This event followed reviews of the lower equipment bay and the upper deck in February. The guidance and control systems, crew compartment, and docking system in March. The extravehicular mobility unit in April. Internal lighting displays and side access hatch in June, and the spacecraft lunar module adapter in June and August. The major result of all these reviews was an entirely new inspection article called, in engineering shorthand, EM, for Engineering Manufacturing Module Mockup, which demonstrated that North American was making progress toward a finished Block 2 design. For several months, Shay had been critical of Block 2 progress. He had complained in June that engineers, besides trying to develop the spacecraft, had adopted a stance of, as long as we're making necessary changes, we might as well introduce these changes to make it better. Therefore, he asked the subsystem managers in Houston and Downey, who were causing some of the problems, to review both Block 1 and Block 2 and eliminate any unnecessary changes. Shay knew there were plenty of subsystems or component problems to wrestle with, without constantly redesigning the lower equipment bay to fit changing components. But, in all fairness, the subsystem managers at North American and the Manned Spacecraft Center were caught in the trap of changing concepts. For example, the cancellation of onboard maintenance in favor of redundant or backup systems in the event of a malfunction resulted in modified parts and subsystems that would no longer fit in the equipment section. But sometimes a change was dictated by troubles that cropped up in supposedly uncomplicated areas. One such nagging problem that arose in 1965 was how to keep the command module windows cleaned. A fiberglass cap with a cork ablator called a boost protective cover was attached to the escape tower and fitted atop the spacecraft to protect the windows during escape tower jettisoning. When tests showed that the cover would crack and the plumes from the escape tower would deposit soot on the windows and possibly cause other damage, North American used a product called Nomex, which is a nylon material strengthened with Teflon, between the fiberglass and the cork layers of the cover to reinforce it. And in areas where problems were expected to arise, they did. 2 of the tanks, one holding oxidizer and propellant for the command and service module's reaction control thrusters, and the other housing reactants for fuel cells that provided electrical power, were in trouble. The Bell Aerospace Systems Company furnished North American with positive expulsion RCS tanks, a system that forced propellant and oxidizer into the firing chamber where the fluids would ignite on contact. The oxidizer tanks kept failing, and Bell kept trying to fix them in an apparently disorganized manner. Eventually, the trouble was traced to the oxidizer, which had too little nitrous oxide in the nitrogen tetroxide, causing stress corrosion or cracking in the tanks. When the nitrous oxide was more carefully specified and controlled, the tanks stopped failing. The hydrogen and oxygen fuel cell reactant storage tanks, tucked in a service module bay, were also developing cracks. By August, Shea was concerned about whether Beech aircraft who supplied them would be able to diagnose and solve the problem in a timely manner for the early flights. But, with the aid of Langley Research Center, the trouble was traced to a reaction of the nitrogen tetroxide to the titanium used for the oxidizer tanks and tubing. Beech simply installed stainless steel components and the problem ended. Shea found that the penchant for unnecessary changes in Block 2 was shared by some of the guidance and navigation system developers. On a visit to Honeywell in May 1965, he learned that 50% of the stabilization and control circuitry was new. 30% was slightly modified, and only 20% was identical with Block 1 wiring. Although he conceded that many of the changes were warranted, Block 2 had been used to justify non-essential circuits as well. Shea believed that the Apollo office was inviting trouble. The changes had reached a point where more time would be lost in trying to eliminate them. Pressure was applied to make sure that North American kept its associate contractors on both the spacecraft and the guidance navigation systems up to date on changes. Interface control documents would be used to prevent this kind of problem in the future. Thanks for listening to this archive episode of the Space Rocket History Podcast. If you are financially able, please support the podcast by going to the homepage, spacerockethistory.com, and clicking on the orange Donate button or the Patreon link. Thanks.